This video is going to discuss limit laws. Now, limit laws are going to help us with evaluation of limits algebraically. Keep in mind that you can always compute a limit, or at least estimate the value of a limit, numerically with a table or graphically. Okay, but again, to find the exact value, we may want to try to utilize these laws. So we're going to assume that A and C are real value constants. So C, we're going to have that be the limit value. So these do not, in general, work with values with limits at infinity. So if you have x approaching infinity, x approaching minus infinity, these generally do not hold. There are instances where they do, but again, generally they don't. Okay, so we have to have A and C be real valued constants, and we also have to have the limits existing individually. Okay, and with this we get the constant multiple law, so we can pull the constant out front of the limit. If we have a limit where we have a sum inside, we can break it up and just sort of quote unquote distribute the limits. Now, limits are an operator, so it's not technically distributing them, but you can think of it for all intents and purposes as distributing. Same thing with multiplication. We can take the limit of the two functions individually and multiply them together. Division, same thing, and then composition also works. I will also mention that if we have powers, we can actually migrate the limit inside of the power and do. So like we could say limit as x approaches c of x to the n. I could also say that this is the same as limit as x approaches c of x all raised to the nth power. That's an exponent law too. There's also root laws as consequences, but please make sure to read any course notes or search other resources for more laws. These are the ones that are most common, so we're going to focus our attention on these. Okay, so we have three problems. We want to determine the value of each limit using these limit laws. So the first one is meant to be more direct and easier for us to use. So first I have the limit as x approaches pi, okay, of the quantity 2 to the x plus sine of x. Now I first need to make sure that what I want to do, what my instinct tells me to do with these limit laws, is to take the limit of each individually. Okay, so I'd take the limit as x approaches pi of 2 to the x, and then add to it the limit as x approaches pi of sine of x. Okay, but I have to check, is pi in the domain of both of these? 2 to the x has a domain of all real numbers, yes, and pi is in the domain of sine because sine has a domain of all real numbers, so we're good. This is okay to do. Then we can evaluate each of these individually. Both these are continuous functions, so I can just substitute the values in directly using the direct substitution property. So I would get 2 to the pi plus sine pi. And sine pi is 0, so this is just 2 to the power of pi. Alright, so now the next one, this one looks a little less friendly, but doesn't mean we can't work with our limit properties. My first question is there any instance where 9 is not in the domain of any of these pieces? So I just want to think through, okay, if I put in 9 here, that'll be positive, so that's fine. So I can take the square root of a positive number. 9 to a fractional power, that'll be fine. If I put it into the natural log, let's see, if I put it into the natural log, that's still positive, so that's okay. And putting 9 in for the 2, that works as well. So, all in all, I am fine. So what I'm going to do first then is use the division law. Okay, so I would write this as the limit as t approaches 9 of the quantity 3 square root t minus 3 plus t to the 3 halves all over limit as t approaches 9 of the quantity 2 natural log of t minus 8 plus t squared minus 1. Okay, and then I can break it up further using the sum rule. Okay, so notationally, and I'm going to have to move this other example down here. So this is going to equal limit as t approaches 9, and yes, I do need all this notation. 3 root t minus 3 plus limit as t approaches 9 of t to the 3 halves all over limit as t approaches 9 of 2 natural log of t minus 8 plus limit as t approaches 9 of t squared minus limit as t approaches 9 of 1. Okay, and then lastly I'm going to evaluate all this. So everything that I have here, these limits are all of continuous functions, and 9 is in the domain of all these, so I can use the direct substitution property right off the bat. So it'll be 3 times the square root of 6 after I simplify, and then 9 to the 3 halves, so I would have to square root it first, so that's 3, and then cube it, so it's going to be 27 after I simplify it, all over 2 times natural log of, this would be natural log of 1, natural log of 1 is 0, so I'm just going to wipe that out, I'll write it out, plus, put in 9, I get 81, and minus 1, limit of a constant is just the constant. Okay, so in the end I get 3 square root 6 plus 27 all over 80. And that would be my answer. The last example that I want to leave you with is the limit of p approaches pi over 2 of 4p plus tangent p. Okay, so our instinct is probably just to write this as equals limit as p approaches pi over 2 of 4p plus limit as p approaches pi over 2 of tangent of p. That's our instinct, okay? But this cannot happen simply because of this second part, okay? This limit does not exist. Tangent of x, tangent of p, whatever it is, has an infinite discontinuity, so it has a vertical asymptote at pi over 2. And one side approaches infinity, the other side approaches minus infinity, so this one does not exist. So in this instance, the limit laws do not apply. Okay, but remember, this does not mean we sit and cry about this. We actually have two other methods. We have either tables or graphs. Okay, so we can always revert to those methods if we find ourselves unable to use the limit laws.